finding, using the matrix, A was equal to 2, 3, negative 3, 2. There's our matrices. And we used it as a matrix of transformation. That means if you have a transformation of x, we were saying that's the matrix A times the vector x. And we let the vector x be x sub 0. We started out with x sub 0, and that was 0 and 1.5, and 0.5. And I'm going to use this notation for those vectors instead. I don't know, it's just quicker, a little more natural for us, I think. So anyway, that was x sub 0. And then we went on to look at all the other vectors. We multiplied this matrix on the left times this matrix on the right, and we repeated that. We've got all our list of vectors. So I'm going to pop those up there. Okay, so that's our list of vectors. And take a look at those vectors. I just plotted the first three vectors on this. You can see that. And so those first three vectors, 0 and 0.5, and the scale here is 1. So 0.5 is here, here's x sub 0, here's x sub 1 would be 1.5 and 1. X sub 2 is 6 and negative 1, 2, 3, 4, 5, 6 and negative 2.5. And then 4.5 and negative 23 was way down here. So that was the x sub 3. So the first four vectors. So take a look at that. Bink, bink, bink. So two things are happening. We've described transformations in the past, right? Where sometimes we have expansions, sometimes we have contractions, we have reflections, rotations. What does it appear is happening here, just at first glance? There's an expansion going on and a rotation. Is that what it looks like to everybody? So, in fact, take a look. Look at this rotation angle and that rotation angle and that rotation angle. Do those look to be similar? Does this look like it kind of, like this vector, x sub 2, does that look like it bisects those two vectors to you? Well, in this particular case, with this particular matrix of transformation, that 2, 3, negative 3, 2 matrix, and it's kind of an interesting matrix, right? I mean, we've got those number sets such that, right, one is a positive 2, positive 3, then negative 3, negative 2. And now that's what our graph turns out to be. And then I graphed the next four on another sheet. So here's what those x sub, I think I started out with x sub 3. See if that'll all fit on there. So x sub 3 is right here. That was 4.5 and negative 23. That was where we left off on the other one. 4.5 and negative 23. But this is going by hundreds, because remember we got out into the thousands. And there's x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, all the way out to here. That might be a little harder to tell that those are those rotations. So let's draw those in too. So this is the first vector here, the second one is here, the third one, we draw the kind of the body of the vector, we get that, and this straight edge. I don't have a long enough straight edge for the last one. That's there. Does that, see that angle? It's kind of hard to tell, but there's an angle there, an angle there, an angle there. It still looks like it's rotating about the same angle. This one's way out there. That's close. Okay. So, yeah, these angles, it's hard to tell when these get smaller, but it still looks like an expansion and a rotation. Let's talk about, well, obviously, you're aware that the 2, 3, negative, 2, 3, negative 3, 2, those numbers are going to have an impact on the magnitude of the rotation and the magnitude of the expansion, right? So, okay, it's not, okay. I guess I gotta stick to this part of the board. Okay. So the next question, I believe, was we plotted those. Now it says to find the eigenvalues of A. So to find the eigenvalues of A, we subtract lambda I. So that means we find the determinant of 2 minus lambda and 3, and negative 3 and 2 minus lambda. And we set it equal to 0. That's going to be 2 minus lambda squared, right? Then what? Plus or minus a negative 9 is going to be plus 9, right? You set that equal to 0. And now to solve for lambda, what are we going to do? You're going to need a lot more paper than that whole sheet, right? So you're going to need to get a separate sheet of paper for this problem. This is going to be a page of work probably. So what are we going to do? You're going to subtract 9 from both sides, aren't you? I guess you could expand this and then use the quadratic formula if you wanted, but it's quick to subtract 9 and then square root, use square root. 2 minus lambda squared equals what? Negative 9. So what are we going to get here, Mariella? Well, there's a difference between a number that doesn't exist and a complex number. All numbers that there's a difference between not existing, there's no possibility, to a number that you have to use your imagination to perceive. Does that make sense? So this has an I and it's going to be imaginary. So we're going to take the rare scoot of both sides. And that's going to be 2 minus, actually, this really gives us what? It gives us the absolute value of 2 minus lambda, doesn't it really? Right? Square root of anything is the absolute value of that something, if we don't know what it is. The square root of negative 9, we know, is 3i, isn't it? So, since the absolute value of 2 minus lambda is equal to 3i, then we get 2 minus lambda would be plus or minus 3i, right? You usually just go straight to plus or minus, don't you? But I just want you to be aware that we're really, the square root of an unknown, it's the absolute value of that unknown, because we don't know if the unknown is positive or negative, right? It doesn't give you what's in the bracket. So anyway, let's add lambda to both sides and then subtract and add 3i to both sides, right? So we'll switch these guys, and this will give us lambda over here. This will be 2, what? Minus 3i and plus 3i. Well, we can just write plus or minus, it doesn't matter. So there's 2 eigenvalues for this matrix, right? Our matrix of transformation. And they're complex. Well, have you graphed anything on the complex plane before? Did you do that a little bit ever? So we have, to graph complex numbers, you have what's called the real axis, and you have the imaginary axis. It's very simple. You go, it's just kind of like when you graph a vector. If you have 3i plus 2j, don't you go 3 in the x and then 2 in the y direction? Well, we go 2 in the real direction, 1, 2 in the real direction, and then we go up 1, 2, 3 in the I direction. So there's 2 plus 3i would be this right here, and 2 minus 3i would be right down here. So this we call the I-axis, and this is the real axis. And so there's your 2 vectors, the 2 plus 3i, and there's 2 minus 3i. Okay? Now, how do you find the magnitude of a vector? don't you find the magnitude of the vector by taking the square root of the sum of the squares of the components, right? So if you have a three-dimensional vector, you all done three-dimensional vectors yet? Magnitude of three dimensionals? So you have like a times the I hat plus b times j hat plus c times k hat, and the magnitude of that is the square root of a squared plus b squared plus c squared, right? Well, what's the magnitude of this vector? I'm thinking that that's what's asked in your handout. It says find the eigenvalues, and then it asks, later it says find the magnitude of the eigenvalues of A. So the magnitude of these, we usually call the magnitude of the eigenvalues, the letter we assign that is R. And R is going to be the square root of, in this case, if lambda is equal to a complex, okay? If lambda is equal to a complex plus or minus bi, doesn't matter which, then the magnitude of that is just a squared plus b squared. See, look, 2 and 3, right? Using the Pythagorean theorem, right? That's all we're doing. Pythagorean theorem's coming up again. So that is the magnitude of this. So in this particular case, what's the magnitude of this, our particular lambdas? They're the same, aren't they? Because it doesn't matter if you go up or down 3. So R, in this case, is going to be the square root of what? 2 squared plus 3 squared, right? And so that's 4 and 9 is 13. It's the rare scoot of 13. Okay. If A is equal to 2, 3, negative 3, 2. We're going to try and put all this together, the expansion and the rotation. So, if A is 2, 3, negative 3, 2, then that's also equal to, if I want to use the rate R, I'm making a kind of a big jump. Remember when you did, when you took a vector and it was in component form and you wanted to change it to polar form? Remember we have x, y coordinates, and then we had r and theta coordinates. Well, this is similar to that. This matrix, I can pull out r from that. If I do this, what would these all have to be if I wanted r to be a coefficient here? Yeah. Wouldn't this have to be 2 over the square root of 13? Right? To make this a 2, this times this would have to be that, right? What am I doing? I'm factoring out the magnitude of the eigenvalue. Or actually both eigenvalues. And this would be what? 3 over radical 13, negative 3 over radical 13, and 2 over radical 13. Does that make sense? If you multiplied this scalar through that matrix, wouldn't you get that? All right? What do you think? Does that make sense? Yes? No? Well, I'm going to show you why we're doing that in just a second. Isn't that the same as if you threw the identity matrix in here, right? Wouldn't the identity matrix times this still give you the same matrix? But if we used associativity, we could multiply I times radical 13, and wouldn't that give us radical 13, 0, and 0, radical 13 times that? That interesting? What makes this really interesting is this is of the form cosine phi sine phi minus sine phi cosine phi, isn't it? Isn't that a rotation matrix? Now, which direction is that going with the negative down here? Isn't that a clockwise rotation? Remember, it's counterclockwise if the negative's up here and it's clockwise down here. You see that? Because this is A, this is B, and this is the square root of A squared plus B squared. That's like the hypotenuse. See? That radical 13 is this length. There's your A, there's your B. So the cosine is the adjacent over the hypotenuse, radical 13, right? Think of 2, 3, and radical 13. The cosine of this angle is the adjacent over the hypotenuse. The sine is the opposite over the hypotenuse. That make sense? So, this matrix right here, which ends up being, we've got two matrices. We've got the matrix basically R0, 0, R, right? And then we have A over R, B over R, minus B over R, and A over R, that form. In this, remember R is the square root of 2 squared plus 3 squared, right? That's what R is. So that's why we've got the square root of 13, 0, 0 square root of 13. And then we have the A is, right? This is 2 over root 13, 3 over root 13, negative 3 over root 13, and 2 over root 13. And that is, if you check it out, so isn't this matrix, doesn't this matrix give you an expansion of radical 13, right? That's an expansion matrix, right? Dilation, right? You have identity with just the same thing here. And then, the cosine of phi, so now what we're getting at, this is a clockwise rotation, and we saw that it was clockwise when we graphed it, right? When we looked at the graph, remember those vectors? They were moving in a clockwise direction, weren't they? See? So that minus being done here rotated it clockwise. And now, the cosine of phi is supposed to be equal to 2 over radical 13, the adjacent over the hypotenuse. We can find phi. We can find that angle of rotation. What's phi equal to? The inverse cosine of 2 over root 13. So, on your calculators, let's find phi. Let's do it in degree mode. So change your calculator to degree mode, find the inverse cosine of 2 over root 13, and we have a good approximation, right? It's an estimate, of course, there isn't an exact value for that. We'll have a pretty good approximation of that angle of rotation. And if you wanted to, you could look at the drawing, and before you even use your calculator, kind of give an estimate. What's that look like? What is that angle there, do you think? They're all supposed to be the same, so look at the two biggest, longest ones are going to be the easiest to tell. You know, this would have been a 90. That looks like it's a little bigger than a 45 maybe, you think? Is that bigger or smaller than 45? Well, you probably already did on your calculator. What'd you get? 56 degrees? Okay. So that gives us a pretty good idea of what to do to figure out how far it's going down. So the magnitude of all those vectors, right? The magnitude of those vectors are increasing by radical 13. Now, the square root of 13 is 3.5 6. What's the square root of 13?
3.6.
3.6. So if you take a look at those vectors, do you think they're about 3.5 times bigger? Well, you could just kind of look at them and say, yeah, look at that. You know, let's take the most kind of the easiest one to do. You can take your ruler even. Say, but let's take this. This is 1, so that's there. 2, 3, 3 apart. Does that make sense? So just by those coefficients, or those entries, we can get an idea of what that matrix is going to do to in a transformation. So let's go back to let's look at the next problem then. It says let A equal 0.3, negative 0.4, 0.40, and 3. So, new matrix. And what's obviously noteworthy on this one, two kind of main ideas here. 0.3, negative 0.4, and 0.4, and 0.3. Okay. We could do the same thing here. We could plug that in. Now it says take x of 0 equals 10, 0. 10, 0. So if x of 0 is equal to 10, 0, we could plug that in. We might want to review that. You guys remember how to do that quickly on your calculators? Oh my goodness. I left my calculator back in the office. Anyway, we don't have to do that. Why don't you try and do that real quickly and just get a few of the vectors. Get a couple. Let's just do the first two. If you get 10, 0, then plug that in and find the transformation. Of course, the transformation on x is defined to be the matrix multiplication of A times that vector x. And so if I multiply A times the vector x, it's pretty easy on the first one. A times x of 0 is going to give us x of 1, and that will be what? This matrix times this vector. So we get this times this is going to be 0.3 times 10 is 3 and 0. It's going to be a 3 for the first row. And then the second row is going to be a 0.4. It's going to be 4. Okay. And then, now let's stop for a second. We know that, now what's the magnitude, how far from the origin is 10, 0? It's 10 units from the origin, right? How far from the origin is 3, 4? Going from 10, 0 to 3, 4, we can just plot those first two quite easily. Five, 10. There's 10, 0, and then there's 5, 3, and 4, right about here. The magnitude of that first vector is 10, obviously. The magnitude of this, 3, 4, this is called a primitive triple. 5. 3 squared plus 4 squared equals 5 squared, right? It's 3 in this direction, 4 in this direction, so the hypotenuse has to be 5, right? So that magnitude of that is 5. So what happens to the magnitude? It's cut in half, right? Can you tell me the angle between those two vectors? Yeah. Remember the inverse tangent? How do you find this? Angle. You could use lots of things. You've got the opposite and the hypotenuse, the adjacent and the hypotenuse, and you've got the opposite and the adjacent. We could use any of them, right? The cosine's kind of nice. And by the way, this is a positive rotation, right? Or it's going in the positive direction, that is, it's going counterclockwise, isn't it? And notice where the negative sign is, up here. So, this rotation, you could use inverse tangent of the opposite over the adjacent. But in the last one, we used the cosine to find phi. We used the cosine of the adjacent over the hypotenuse. Remember? A over R. Right? R, we don't even need to know our eigenvalues to know that R is going to be 1/2, isn't it? Isn't the magnitude of R going to be 1/2? But anyway, A over R is 3 over 5. Oops. Yeah, 3 over 5 should be that. And 3 over 5. That should be right. What is the inverse cosine? I'm sorry, inverse cosine. 3 over 5.
53.1.
53.1 degrees. That's in a clockwise direction, of course, right? You always want to indicate clockwise or counterclockwise. So the truth is, we could just, if you wanted to, aren't these getting cut in half? So we could just cut that in half and then just rotate it 53 degrees. Pretty sure the next value is going to be, that angle. We'll take that angle and rotate it. That's going to be about here. It's going to be half of that. Yeah, there's the next value right about there. 100, maybe right about here, right? And then the next one, rotate again, cut it in half. It's going to be right about here. What's happening? What's the difference between these and the previous ones? Yeah, these are kind of spiraling in, aren't they? And the other was spiraling out, right? So when computers generate fractals, it's really a bunch of transformations. And instead of using a matrix, they just use a lambda. They use an eigenvalue to multiply by. But remember, A times a vector is equal to lambda times a vector. That's how all this started, right? A times a vector is equal to lambda times the vector, right? So if you use the right lambda, you're going to get this, instead of multiplying by this matrix over and over again, there's going to be eigenvalues that you can multiply by and get the same thing. So the eigenvalues are going to change that vector, just like the matrix would change the vector. So fractals are based on complex numbers. The spiraling is a complex number. Lambda is going to be complex here, okay? Because of the way this is set up. These spiraling, how fast does it spiral in, or how fast does it spiral out? It's just programmed to base the color of any particular vector on how it spirals. Whether it spirals out or whether it spirals in. And in the early days, that was kind of the idea, was things would turn black if they spiraled, well, I can't even remember. I think spiraling out made them turn black. And if they spiraled in, they're different, Anything that spiraled out turned black. Everything that spiraled in had various colors. Anyway, really interesting to have the drawings based on speed of rotation. Okay. I'm not going to go on and get the other x's, but I want to find the eigenvalues of A, and we already have an idea, we already know without this, but I want to rewrite that A then as the product of its magnitude change and its rotation. Okay, the two matrices. So, what is the eigen? How do you find the eigenvalues? We go -3 minus lambda, or 0.3 minus lambda, and 0.3 minus lambda. We get -0.4, and we get 0.4. Oops. We take the determinant of that and set it equal to 0. So the determinant of that be, of course, 0.3 minus lambda squared plus, I'm just going to write 0.4 squared, right? And that's equal to 0. If we subtract this from both sides, we get 0.3 minus lambda squared equals the opposite of 0.4 squared. We know that's 0.16. And then, of course, when you take the rare scoot of both sides, you get 0.3 minus lambda is equal to, now the negative gives us our I, and our 0.4 squared, the square root of that is just 0.4. But we know this really needs absolute value bars, but we usually just throw that plus or minus on that instead, right? Now add lambda to both sides, subtract and add 0.4i to both sides, and we get lambda is equal to 0.3 plus or minus 0.4i. And this is not the I vector, right? This is I, the imaginary I. This is I in different ways, right? So anyway, and now if we had used the formula in eigenvectors or eigenvalues, so eigenvalues, if it's of the form A, B minus BA, this type of matrix, right? That's the two we've looked at for complex eigenvalues. If it's of this form, the eigenvalues are going to be A plus or minus BI. Okay, we'll show that in just a minute. And what's R going to be? R is going to be, it's the magnitude of lambda, is going to be the square root of A squared plus B squared, right? And what is phi going to be? Phi, the rotation, is going to be the inverse cosine of A over R. Okay? This is kind of the basic formula for all these matrices of this form. Okay? I didn't go ahead and show you this, but isn't the magnitude of lambda here, for this particular one, how do I find the magnitude of this? It's going to be 0.3 squared plus 0.4 squared, right? Let's go ahead and finish that. Lambda was equal to 0.3 plus or minus 0.4 I. So the magnitude of lambda that we call R is equal to the square root of 0.3 squared plus 0.4 squared, right? Which is 0.09 plus 0.16, right? Which is 0.25. The square root of 0.25 is 0.5. Just one. This is 1/4. 1/2 times 1/2 is 1/4, right? So it's 0.5, not 0.05. That's R. And plus we knew that because didn't we go from a magnitude 10 down to a magnitude 5? So we knew R was 1/2 already, didn't we? So, does that make sense? We got an idea. So, check it out, obviously. Since these were smaller than 1, right, they're all smaller than 1, what happens? It spirals in, right? If they're bigger than 1, it's going to spiral out. What if one of them is bigger and one of them is smaller? That might hurt, right? What if this is bigger than 1 and this is smaller than 1? What is R? Remember, R tells you whether it goes in or out. If R is less than 0, less than 1, and R is always positive, right? Because it's the positive square root. So if R is less than 1, it spirals in. If R is greater than 1, it spirals out. Okay? Goes to 0, goes to infinity. Right? So let's just verify that. I think that's all I have thoughts for doing right now. We didn't do any eigenvectors.
Would it just be r less than 1 or the absolute value of r?
R is the absolute value of 1. You could do this if you wanted. Why don't we do this? The absolute value of lambda. Because that's what R is. It's already an absolute value, remember? It's the magnitude of it. The magnitude is positive in this case. That's the square root of a squared plus b squared, right? Right here. If it's the square root of a squared plus b squared, if either one of those is bigger than 1, what's going to happen? If this is, let's say this one's a 1 and this one's a 0.5. That's going to be 1 squared plus 1/4, which is 1 1/4, and the square root of 1 1/4 is bigger than 1, isn't it? So if either one of them is bigger than 1, it's going to spiral out. Does that make sense? And we can rewrite it always too. You can always rewrite the matrix as a magnitude matrix. This is a R0 and 0R, right? And the other one's going to be the inverse cosine of, it's going to be the cosine of A over R, the sine of B over R, and that, to make it a counterclockwise, that would be minus, and then the sine of B over R, and the cosine of B over R. And this is what A will equal, right? This is what A is equal to.
Wouldn't that be cosine a over r?
Yes, thank you. That's an A over R. BB, AA. Okay? AA. So, there's your rotation matrix, and there's your dilation or contraction, right? Matrix. Whatever R is. Okay. In general, okay, well, I don't want to find the eigenvectors for that one for fractions. It's a little more of a pain. I'm going to make one up. Let's talk about how to find the eigenvectors again, which we've done. Do it with A and B. I should just make up a matrix. Did we do it? I had another problem here, but I didn't get it. Well, let's make up an expansion matrix. So tell me, just give me a matrix with integer values, but no decimals. What do we want? Pick a couple numbers. Go ahead, Jacob. Pick 1,
2.
and 2, and negative 2, 1, right? That's how you make a rotation matrix then. Or you can make that the negative and that the positive. So A equals 1, B equals 2, right? And so what's what are our two eigenvalues going to be? 1 plus or minus 2i. That's it. It's that quick. But now let's find the eigenvectors for those. And that's a little different. If it's in this nice, convenient form, aren't we going to have to take, don't we row reduce? Remember, this is A, this is matrix A. We need A minus, we're solving basically. We want A minus lambda I. We want that equal to 0, right? We need to solve this. That's what we're solving, right? To find x. X are our eigenvectors. So we solve that homogeneous equation. So we get 1 minus 1 plus 2i and 2, and negative 2, and 1 minus 1 plus 2i. This, and I guess we can put the zeros there. We don't need to, but we put the zeros there. And that is our homogeneous system. Now, how do we solve that? And this is for only, by the way, this is for lambda equaling 1 plus 2i. We have to do this twice, don't we? Because we have another one, lambda 1 minus 2i. So we have to go through this process twice. But let's go ahead and simplify this. I'll make it a little smaller here. 1 minus 1 plus 2i. Distributing the 1 gives you 0 there and a minus 2i. So we get minus 2i and 2. And we get minus 2 and that drops again and we get minus 2i. Same thing, right? Do you want to do row reduction? It's really fast when they look like that. All you have to do, don't you want to, if these two are the same, I'd multiply everything by I. What happens if you multiply everything, row 2 by I times row 2. What are we going to get? Negative 2i, 2, 0. And that's going to be negative 2i. And I times this is going to be I squared is negative 1. And negative 2 times negative 1 is 2. So what happens? This is basically going to get zeroed out, isn't it? They're identical. So we just subtract row 1 from row 2, and we get negative 2i, 2, and 0, and 0, 0, 0. So we have a free variable here for x of 2, and what's x of 1 equal to? Well, negative 2i x of 1 plus 2x of 2 equals 0, right? So if we, let's just add 2i x of 1. Or we'll change the sign. We'll subtract it and change the sign. So that's 2i x of 1 is equal to 2x of 2, right? That make sense? Divide both sides by 2i to get 2x of 1 by itself. And we get x of 1 is equal to, what happens? We get x of 2 over I. Now, we want to rationalize that. What do you do to get rid of the I? How do you rationalize that denominator?
Well, how about your negative?
Well, if I subtract 2
Oh,
from both sides, okay, I can put a negative there and a negative there, and then you can have all the negatives, or you can just divide by negative 1. Aren't we going to multiply both sides by our numerator and denominator by I to get rid of that? Now, x of 1 is equal to what? Well, what does this give you in the denominator?
Just be 1.
Negative 1. And so you're dividing by a negative 1. That becomes negative I times x of 2. And what was x of 2 equal to? It was equal to itself because it was the free variable. Right? So the eigenvector for this lambda is what? This eigenvector is negative I and 1. That's the eigenvector for that particular eigenvalue. Okay? Does that make sense? The opposite of I here and 1 here. All right, that's it for today. It's only Thursday, right? That leads us right into really tomorrow's stuff. Okay.